Okay, so here in this problem, we have saturated steam that's being used to heat a stream of ethane. So first let's draw this out. So we have here our heat exchanger, and we have saturated steam at 2 bar, gauge pressure. So P total is going to equal P gauge plus P atmospheric. So 2 plus 1, where our steam is actually at 3 atm. So we have some mass flow rate of steam here at 3 bar. 3 bar. And this is also going to be exiting at 3 bar. But it will be heated to, it will be condensed and leave the heat exchanger at 27 degrees Celsius. So this condenses. And then we have our ethane stream that enters the heat exchanger at 2.5 bar. And a rate of 795 cubic meters per minute. So we know the volumetric flow rate. We will need to figure out the mass flow rate. And we know it's heated at constant pressure up to 93 degrees Celsius. So enters at 16 C and leaves at 93 C and 2.5 bar. So we need to figure out how much energy should be transferred to ethane to heat it from 16 degrees Celsius to 93 degrees Celsius. And we are given the specific enthalpy of the ethane stream entering and leaving the heat exchanger. So now we're going to start with our open system energy balance. So change in enthalpy plus change in kinetic energy plus change in potential energy is going to equal Q plus W. So we don't have any kinetic energy change here, no potential energy change here, and no work to the system. So delta H is going to equal Q here. And that is going to equal the mass flow rate of the ethane times the specific enthalpy out minus the specific enthalpy in. So we know we can calculate the delta H, which is going to equal the heat that we're looking for here. But what we need is our mass flow rate. So we're given the volumetric flow rate. We just need to solve for the mass flow rate using ideal gas law. So we know that V is equal to 795 meters cubed per minute. And we know that PV is equal to nRT. So N is equal to PV over RT. And if we want that in terms of mass flow rate rather than mole flow rate, we know that the mass flow rate is going to be equal to PV over RT just times the molecular weight of ethane. So the mass flow rate is going to be equal to, so our pressure is 2.5 bar times the volumetric flow rate is 795 meters cubed per minute over 0.08314 liters times bar over mole per Kelvin times our temperature is 273 plus 16, so 289 Kelvin. And do our units check out? Bar, Kelvin, Kelvin. We need our volume up here to be in terms of liters. So 1 cubic meter is equal to 1,000 liters. So now our units check out. Oh, and we need to multiply by our molecular weight, which is 30.07 grams per mole. And let's put this in terms of kilograms. So 1,000 grams per kilogram. And let's multiply all this out. So we end up getting 2,487 kilograms per minute. So now we know our mass flow rate, and we know our specific enthalpies into and out of the system. So now we can solve for delta H, which is the same thing as Q. So 2,487 kilograms per minute times the enthalpy out of the system. Let's see. Out is 1,073 kilojoules per kilogram. And then entering the system at 16 degrees Celsius, it's 941 kilojoules per kilogram. So this is going to give us 328,284 kilojoules per minute. And we could put this in terms of kilojoules per second in order to get kilowatts. So multiply by 1 minute per 60 seconds, divide by 60. That gives us 5,471 kilojoules per second, which is equal to 5,471 kilowatts.